All right, get ready, because today we're going deep, really deep into the world of atomic physics. You've sent us some really interesting excerpts from this physics textbook,
Oh, yeah.
and
Yes,
we're
ma'am.
going to break it all down, all the major discoveries and the models that scientists came up with as they were trying to figure out what the atom is all about.
It's a fascinating journey,
Yeah,
to see how our picture of the atom has changed over time
exactly.
from these really basic ideas to some pretty complex theories.
Yeah, so whether you're like studying for a big exam or maybe brushing up on some high school physics or just, curious about what makes up, well, everything,
Right.
get ready for some serious aha
For
moments.
sure.
We're about to enter a world where things, well, they're not always as they seem.
Yeah. For centuries, people
Yeah.
thought that the atom was this, like, tiny little indivisible particle, like the
Yeah.
smallest thing you could possibly have.
Right.
Turns out it's a lot more complicated than that.
So let's start with the basics. We know atoms have these negatively charged particles, electrons.
Right. And for a long time, scientists thought those electrons were just kind of embedded in this positively charged, I guess you could picture it like a pudding.
Pudding. Okay, now I'm intrigued and kind of hungry. So are the electrons like plums scattered throughout this plum pudding model?
You got it. That's exactly it. That was J.J. Thomson's idea back in the late 1800s.
Okay.
Good starting point, but of
Yeah.
course,
Yeah.
like any good theory, it needed to be put to the test.
Right. And that's where Ernest Rutherford and that famous gold foil experiment come in.
Right.
What was he even trying to do with that?
Well, his team was basically shooting these tiny positively charged particles, alpha particles, at a thin sheet of gold foil.
Okay.
Kind of like if you imagine throwing marbles at a piece of paper,
Right.
you'd expect most of them to just pass right through.
Yeah, that makes sense. If the
Yeah.
atom is like this evenly distributed pudding, right?
Exactly. But here's the thing. That's not what they saw. Most of the alpha particles did go straight through, but a few of them, they were deflected and at some crazy angles.
Really?
And some even bounced straight back.
Whoa, hold on. Bounce back like they hit a wall inside the atom.
It was total shock.
Hmm.
This meant that the positive charge in the atom, it wasn't spread out evenly like in that pudding model.
Okay.
It had to be concentrated in this tiny, super dense core,
Hmm.
which is what we now call the nucleus.
Okay, so that's a game changer. So, goodbye, plum pudding model, and hello.
The planetary model.
All right.
Rutherford proposed that the electrons were actually orbiting this nucleus, kind of like planets around the sun.
I can see why. It's such a clear image.
Right.
But I'm guessing there were still some problems with this model.
Well, yeah. Remember, we're talking about charged particles here.
Right.
And according to classical physics, if an electron is orbiting the nucleus, it should constantly be giving off radiation, losing energy, and basically spiraling inwards.
So the atom should just collapse on itself.
Basically, yeah. And to make things even more confusing, scientists had already seen that atoms only give off light at very specific wavelengths, what we call line spectra, and the planetary model just couldn't explain that.
Okay, so this model explains the nucleus, but can't explain why atoms are stable or how they emit light. Atomic physics needs a hero.
Well, it got one. Niels Bohr.
Oh, yes, the quantum revolutionary. So what did Bohr bring to the party?
Bohr had this radical idea. He proposed that electrons, they can't just exist anywhere around the nucleus.
Okay.
They can only be in specific energy levels, and these levels, they're quantized, like steps on a staircase.
Oh, I like that. So electrons can be on one step or another, but not in between.
Exactly. And here's the key. When an electron jumps from a higher energy step to a lower one, it releases energy, and that energy comes out as light.
And since those energy level jumps are very specific, the wavelengths of light that are emitted are also specific, and that explains those line spectra.
Exactly. Brilliant, wasn't it? Bohr's model, it not only explained why atoms are stable, but it also finally made sense of those spectral lines that had scientists baffled for so long. It really was a huge step forward.
Yeah.
And, it earned Bohr the Nobel Prize in Physics a couple years later in 1922.
Wow.
And the thing is, this whole idea of explaining these line spectra,
Yeah.
it wasn't just some theoretical thing.
Yeah.
It had like real-world applications, you know? Like it helped us understand why different elements give off different colors of light.
Yeah.
Which is something you probably saw back in like chemistry class. Remember those flame tests?
Oh, yeah, with all those cool colors.
Right.
So something that seems so abstract can actually help us understand the world around us.
Exactly.
That's awesome. But I'm getting the feeling there's another but coming.
Well,
Yeah.
as groundbreaking as Bohr's model was, it did have some limitations.
Right.
It worked amazingly well for hydrogen, because it just had that one electron.
Right.
But when scientists tried to apply it to atoms with more electrons, things got a little messy, to say the least.
So more electrons, more problems.
Pretty much, yeah.
I'm guessing those neat energy levels in the whole staircase analogy started to break down.
Exactly.
Okay.
And there was this other thing that Bohr's model couldn't really explain, the intensities of those spectral lines. Some were brighter than others, meaning some electron transitions were happening more often.
Okay.
But Bohr's model didn't say why.
So it's like having a map that shows you the cities but doesn't tell you how busy the roads are between them.
Yeah, that's a great way to put it.
Okay.
And so this is where things take another interesting turn.
Mm-hmm.
Remember Louis de Broglie?
Yeah, vaguely.
Well, he came along and kind of threw a wrench in the works with this whole idea of wave-particle duality.
Wait, wave-particle duality? Okay, now we're getting serious. Are we saying that electrons act like waves now?
Yep, that's exactly it. De Broglie proposed that electrons, these tiny little particles we've been talking about, well, they can also behave like waves. It sounds kind of crazy, I know.
Yeah, a little bit.
But think about it.
Okay.
We already know that light can act like a wave.
Right, like making those interference patterns.
All right. But it can also act like a particle, carrying energy in those little packets we call photons.
Yeah, I remember.
So de Broglie was basically like, hey, if light can be both a wave and a particle, why not electrons too?
Okay, I see where he's coming from. But how does that fit into the picture of the atom?
Okay, imagine a guitar string.
Right.
When you pluck it,
Yeah.
you get that standing wave
Right.
with a specific wavelength.
Right, with those fixed ends and the peaks and troughs all lined up.
Exactly. So what de Broglie suggested was that those electron orbits that Bohr had come up with, well, they weren't just random.
Okay.
They were actually like standing waves.
Oh.
The electrons could only exist at specific distances from the nucleus where the wave pattern would fit perfectly.
So those quantized energy levels, they weren't just some arbitrary rule. They were actually a consequence of the electrons behaving like waves. It's all starting to come together.
Right. Pretty neat, huh? De Broglie's insight, it helped explain those quantized orbits, and it kind of paved the way for an even deeper understanding of atomic structure.
Wow.
But to really get a handle on the atom, we got to move beyond Bohr's model and into this really strange world of quantum mechanics.
Okay, bring on the mind-blowing stuff. What does quantum mechanics tell us about these electrons?
Well, it tells us that we need to kind of let go of this idea of electrons as these tiny little balls that have a definite position and speed, you know?
Okay.
We had to start thinking of them more like probability clouds, basically fuzzy regions where we're more likely to find the electron.
Hold on, probability cloud sounds like we're entering a whole new level of weird here.
Yeah, it gets a bit strange.
So instead of tiny planets orbiting the sun, we've got these fuzzy clouds?
That's the idea. These probability clouds are described by these mathematical things called wave functions. And they tell us the chances of finding an electron in different spots around the nucleus.
Yeah.
The denser the cloud in a certain area, the higher the probability of finding the electron there.
So we've gone from this neat and tidy picture of electrons in specific orbits to this fuzzy, uncertain world of probability clouds. Whatever happened to certainty?
Well, in the quantum world, certainty kind of goes out the window. It's all about probabilities.
Okay.
And this shift in thinking, it was huge. It helped explain those spectral line intensities that Bohr's model couldn't quite handle.
Right.
The shape and density of these probability clouds, they actually tell us how likely an electron is to jump between different energy levels. And that affects the brightness of those spectral lines.
Okay, so these probability clouds, these wave functions, they're not just theoretical mumbo-jumbo.
No, not at all.
They actually have real-world effects on how we understand things like those spectral lines.
Exactly. And this is just the beginning when it comes to quantum mechanics.
Oh, boy.
It's this whole crazy theory that governs how things work at the atomic level.
It sounds like quantum mechanics really revolutionized how we think about the fundamental building blocks of reality.
It did. And it still shapes how we understand the universe today.
That's amazing.
But, you know, we've covered a lot of ground here.
Yeah, we have.
Maybe it's time to bring things back down to earth a bit and talk about some of the real-world implications of atomic physics, you know?
Yeah, let's do it. I'm curious to see how all this knowledge about atoms and this crazy quantum behavior actually affects our lives.
Oh, in so many ways.
It's amazing to think something so tiny, something so fundamental to everything, can actually have such a huge impact on how we live our lives.
It really is. I mean, atomic physics, it's not just some abstract idea, you know, stuck in textbooks and labs.
Yeah.
It's the basis for so many technologies we just use every day without even thinking about it.
Okay, so give me some examples. What kind of cool stuff has atomic physics brought into our world?
Well, how about lasers? They might seem kind of sci-fi,
Yeah.
but they really show how we've figured out how to harness the power of atomic physics.
Okay, I'm listening. How do lasers and atoms connect?
Well, lasers actually use those super precise energy transitions of electrons in atoms that we were just talking about.
Oh, right.
Remember how electrons can jump between those energy levels and release light?
Yeah, like those spectral lines that helped us figure out the structure of the atom in the first place.
Right. So in a laser, what we're doing is we're basically exciting a whole bunch of atoms, getting their electrons all pumped up into a higher energy state.
Okay.
And then when those electrons drop back down to a lower energy level,
Yeah.
they release a ton of photons, and all those photons have the same wavelength, and they're all traveling in the same direction.
So it's like a synchronized electron jump party.
Pretty much.
And that's what creates that super focused beam of light that we see in lasers.
You got it. And, laser beams are used in so many things.
Yeah, I bet.
From scanning groceries at the checkout
Right.
to fiber optic cables that make the internet work.
Wow. So every time I scan my loyalty card at the store, I'm basically seeing atomic physics in action.
That's right.
That's pretty cool. What other amazing things has atomic physics given us?
Well, let's talk about atomic clocks.
Okay.
These are like the ultimate timekeepers, right?
Yeah.
And they work because of those incredibly precise frequencies of radiation that atoms give off.
Hmm.
They're so accurate.
Yeah.
They lose less than a second every 100 million years.
Seriously. That's mind-blowing. Why on earth would we need clocks that are that accurate?
Well, for one thing, they're essential for GPS.
Oh, right.
GPS relies on this network of satellites, and each one has an atomic clock on board to send out those super precise time signals.
Guy.
Without those clocks being incredibly accurate, our navigation systems would be totally useless.
So all those times I've used my phone to find my way home,
Right.
I actually have atomic physics to thank for that.
You got it.
Mm.
Atomic physics isn't just about understanding the universe.
Yeah.
It's actually about making our lives better in very concrete ways. And hey, we can't forget about medical imaging.
Oh, of course, like MRI and PET scans.
Exactly. Those rely on our understanding of how atoms interact with things like magnetic fields and radioactive isotopes.
Yeah.
So we can create these detailed pictures of what's going on inside the human body.
It's amazing how atomic physics has completely changed how we approach healthcare.
It really has.
So from the everyday things we do to, life-saving medical technology, atomic physics is everywhere.
It really is.
It just goes to show how important basic scientific research is.
Absolutely.
Like pursuing knowledge just for the sake of understanding.
Right.
You never know where those discoveries might lead.
You never know.
It's really inspiring.
It is. Our journey into the atom has taken us from those early models
Yeah.
to all the weirdness of quantum mechanics.
Definitely.
And we even got to see how this stuff actually plays out in the real world.
It's been quite the adventure.
It has.
But, before we wrap up, I have one last question for our listeners.
Okay.
Something to really get them thinking.
Go for it.
We've talked about how atoms are mostly empty space.
Right.
So if that's true, what does it actually mean for something to be solid? It's something to ponder, and it might even change how you look at the world around you.
It's a great question, and it just goes to show how much we still have to learn about the nature of reality.
Well, on that note, we'll leave you to contemplate the mysteries of the atom and the amazing universe it helps to create. Thanks for joining us on this deep dive into the fascinating world of atomic physics.